So in this video we're going to go over some basic exercises and calculations involving the concepts with electromagnetic fields and electromagnetic waves. So here, just as a warm-up, in our first problem we have just a relative velocity problem of a rocket cruising by a laboratory, and the question is, what is the proton's speed and angle from the y-axis according to the laboratory frame and according to the rocket frame. So this is just really a very basic, like chapter 1, chapter 2 type of calculation, but just to get us in the frame of mind of these shifts in reference frame when going from lab frame to some other frame for electric fields and magnetic fields, which is what we're soon going to be getting to. So if you consider yourself on a train and you throw a baseball, the speed of the baseball, well, at least the velocity of the baseball according to somebody on the ground, is going to be equal to the velocity of the baseball according to you on the train, plus the velocity of the train according to the person on the ground. So you can translate all of those various quantities into subscripts and say that the velocity of some object C according to a person in reference frame A is going to be equal to the velocity of that object C according to some other reference frame B plus the velocity of reference frame B according to reference frame A. So again, you could just exchange baseball, train, and ground for those from the last example. So in this case, the velocity of the proton according to the rocket is going to be equal to the velocity of the proton according to the lab plus the velocity of the lab according to the rocket. So that's what we're going to be utilizing in part B here. So in the lab, we're already given this information. So we have the speed, which just comes from the Pythagorean theorem, and can plug those in. Notice I did this little cute factoring out of a 10 to the 6th meters per second on the outside to lessen my calculations, and we get 1.99 times 10 to the 6th meters per second for that speed. And for the angle, just take the arctan of the x component over the y component and get the angle. Notice the x component over the y component as opposed to the other way around, which is we usually do it the other way around, but they're asking us for the angle from the vertical, from the y-axis. So that's why we did it that way. Now, for part B, the velocity of the lab according to the rocket frame, well, we have that, but we're trying to get the velocity of the proton according to the rocket frame. So we need a way of stating the velocity of the lab according to the rocket frame. Well, we know the velocity of the rocket according to the lab frame. That was given to us, 10 to the 6th meters per second. But we need velocity of lab according to the rocket frame. Well, remember Einstein's first postulate: the laws of nature must have the same form in all inertial reference frames. And this rocket is not accelerating, so it's an inertial reference frame, so it behaves as its own rest frame, so to speak. So according to somebody in the rocket, the lab is at rest, or the rocket is at rest, and the lab is what is moving. So the velocity of lab according to the rocket is going to be minus what we had for the velocity of the rocket according to the lab. So that's what ends up going into this equation right here. So upon doing that, we have a new equation for the velocity vector of the proton according to the rocket frame. And now we can do the same thing before, Pythagorean theorem, and get our speed of the proton according to the rocket frame, and also the angle with respect to the vertical, and in this case 16.2 degrees. So it shouldn't be surprising that that angle is a bit less because of the fact that the rocket is, in this case, moving. So in the next problem, we have a figure showing an electric and magnetic field. In frame A, a rocket in frame B travels parallel to one of the axes. The question is, in which direction must the rocket move in order for scientists to measure scientists in frame B to measure the magnetic field to be greater than that in frame A, equal to that in frame A, or less than that in frame A. Now it turns out that there are a little bit of sneaky solutions here, things to think about. So we start off with the equation for transforming the magnetic field measurement to a different reference frame. So that equation is that the magnetic frame according to some, the magnetic field due to some measured in some new reference frame is equal to the magnetic field measured in another reference frame minus 1 over c squared times v cross E, where E is the electric field according to the old reference frame, and v is the velocity of the new reference frame according to, as measured in, that is, the old reference frame. And we have that 1 over c squared factor in there as well. So, well, let's consider just kind of what seems to be the easy solution. In other words, how do we make this magnitude of the magnetic field in frame B bigger than that in frame A? Well, that'll work out if the value of this cross product ends up being negative. That'll end up killing the negative sign in the to the left of the 1 over c squared, giving us a positive, so that'll give us B being greater than BA. So V cross E, well, let's see now. E is up, and so just thinking about our right-hand rule, well, V cross E is going to end up being negative. That is toward the, so if V is toward the left, then V cross E is going to end up being negative, that is into the page, that is the negative z direction as opposed to the positive z direction, and that would end up giving us that the magnetic field in frame B that would be larger than that in frame A. So it seems like that's the end of the story, and we move on to part B. However, there's actually another solution to this, because notice they're asking for the field strength. They don't really care about pluses and minus signs. There's another way of doing this, of getting B sub B greater than B sub A. Can you think of it? So if you need a few minutes, pause the video. So if you've thought of it by now, then here it is. What you can also do is you can actually move toward the right at a large enough speed such that V cross E over c squared is at least equal to twice the magnetic field measurement according to frame A, because that will end up not only canceling out B sub A, that'll end up giving you another factor of B sub A in the minus direction, and if you move even faster, then it ends up being more than that in the minus direction, but again, we're focused on magnitudes, so in that case, the field strength as measured in frame B would end up, in that case, again, being larger than the field strength as measured in frame A. So that's the type of thing that it's a good idea to think about, and I think this was not intended when the problem was made, given that it is exercise 2, and those are usually the types of things that you're supposed to be able to do in your sleep, but nonetheless, it turns out that's one of those things you got to consider. And it's also not mentioned in the author's solution manual. So nonetheless, if you come across something like this on the AP exam, you should definitely make a note of it. Part B. This case, it actually is straightforward. If the velocity vector is either up or down, then the cross product will be 0 because you're going parallel to the electric field. Two vectors that are going parallel or anti-parallel will have 0 cross product. So then B sub B vector is B sub A vector, and you would also end up having the magnitudes be the same as well. Now, you could probably also find a way of making it work out by having something weird going on and having the direction of V cross E being just right so that the magnitude of everything ends up kind of working out. In other words, it would have a combination of X and Y components that would end up making it so that when you do the Pythagorean theorem, you would get something that's the same as B sub A as well. I did not feel like doing that calculation, but I will tell you that yes, there are other ways of moving here in directions that have both positive and both X and Y components, except, look at the problem, it says it travels parallel to one of the axes. So even though that is true, it's not valid for the way the problem was stated. So now we can be happy in moving on to part C. Well, what do we have in order to make the field measure strength less than that in frame A? Well, it's going to be moving toward the right. Moving toward the right will make this cross product positive, and you'll be subtracting a positive number, and that'll be okay as long as you're not moving to the right too fast. In other words, kind of the opposite condition of what we noted in part A. So as long as you're not going too fast, you're not going to end up making this too negative. So those are the three possible situations for this problem. So in the next problem, we're told scientists in a lab frame create a magnetic field, an electric field of 1,000,000 volts per meter in the direction of the positive z-axis in a region of space with no magnetic field. So the question is, what are the fields in the reference frame of a rocket traveling in the positive x direction at 10 to the 6th meters per second? So in this case, we have these two equations for how the electric and magnetic fields transform, and we have our givens. So now it's just time to plug stuff in. First, for the electric field, we get E sub B equals E sub A plus V cross B. I actually would recommend memorizing this equation because it looks so much like the Lorentz force equation for the motion of a charged particle in a combination of electric fields and magnetic fields. You have a QE contribution and you have a QV cross B contribution. So that's actually something that's relatively easy to remember. So now we plug in our givens, and we get that because of the fact that the magnetic field is 0, we end up getting 1 times 10 to the 6th volts per meter in the positive z direction. That is the k-hat direction. Now, for the magnetic field, we have a different situation. So we plug in our numbers, and we get that in this case, we actually do get a result for the magnetic field, a non-zero magnetic field. In other words, the magnetic field, even if it's 0 in one frame, it is not necessarily 0 according to a different reference frame that is moving through an electric field at some velocity. So in the fourth exercise, we have similar ideas as before, this time taking place at an angle. So according to scientists on the rocket, what angle does the electric field make with the axis of the rocket? So we have our givens. We write down the electric field vector that we notice here. Notice that what I did in order to do this is I simply wrote down the magnitude of the vector and I multiplied it by a unit vector going in the direction of that vector. So that's a 45-degree angle. Well, I can do sine and cosine of 45 degrees, so that's how I got my unit components there. And we also have our magnetic field vector as well. It's pointed out of the page, and if we assume x is to the right and y is up, then z is out of the page. So this is good so far. And our velocity vector is in the positive x direction, 1,000,000 meters per second. So here's where we're at so far. Again, our E-field transforming equation, and you plug in the numbers just like before. And let's see, we have an I cross K right here. Well, I cross J is K, J cross K is I, K cross I is J, so I cross K, putting those in reverse, must be negative J. So that is indeed what we end up getting. And when we combine like terms together, this is our E-field direction. So in order to figure out angles, we take the arctan and get a 16.3 degree angle above the horizontal. So in this problem, we have another rocket, and the question is, what are the electric and magnetic fields according to an earthbound scientist? So in this case, we think, oh, are we going to have to end up transforming the equation, subtracting instead of adding, or that sort of thing, and flipping the equation around? Well, turns out the answer is no, because remember, Einstein's first postulate, which in a lot of ways is really just a restatement of Newton's first law, is that, well, according to the rocket is at rest. So Earth is moving toward the left at 2 times 10 to the 6th meters per second. So we have the electric field and magnetic field measured, and the velocity of the Earth field according to the rocket field is negative 2 times 10 to the 6th meters per second I hat. So here we go. and we have the same equations as we've been dealing with so far. So to figure out the electric field according to Earth, we have this result. Plug in our numbers, and we get -1 × 10⁶ volts per meter in the k direction.